Greeting and welcome to our fifth lecture about the ergodic decomposition. The ergodic decomposition is the first sequence of lectures that I'm recording for the ergodic theory course, and the fifth is the last of the series. Let's first of all recall the setup that we have. We're working over xd, which is a compact metric space. We have a continuous transformation from x to x. If it simplifies things, you're free to look at homeomorphisms. Sometimes they do simplify things a little bit. The invariant measures on the Borel sigma algebra Mx was denoted by M sub t, and we know that this set is convex, compact, and not empty. Convex, compact, not empty sets have their extremal points, and the set of extremal points was denoted by E sub t. The theorem that we finished proving last time, which is named the ergodic decomposition theorem, says that any invariant measure in MT is an average of extremal measure. The extremal measure in this integral is represented by nu. Nu varies over all extremal measure, E sub t. Lambda is some probability measure. Given any probability measure on a set, like E sub t, the integral will give you, if you want, like the average, the expected value, the center of mass. It goes in by different names. And for an appropriate choice of lambda, you'll get mu. Again, the ergodic decomposition tells us that for any mu, there is a probability measure on the set of extremal points, such that this integral represents exactly mu. So this highlights the importance of understanding what the extremal measures actually are. Let's first look at a few examples. It's always good to keep a few examples in mind as you listen through the lecture or read through the notes. One standard example, we've seen it before, is if you look at the space as the closed 0, 1 interval, and you simply take the squaring transformation on it, then the extremal measures are only delta 0 and delta 1. Delta 0 is the measure supported at the point 0, so it gives measure 1 to a set that contains 0 and measure 0 to all other sets, and similarly delta 1 is the measure supported at the point 1. The set of all invariant measures is itself an interval, or at least looks like an interval, where it's the convex combination of delta 0 and delta 1. This convex combination is given here, where p is some point in the closed interval 0, 1. As a second example, you can look at an irrational rotation. We'll go back to that towards the end of the lecture. We'll get back to that then. An irrational rotation has only one invariant measure. Now let's think about this situation for 1 second. The extremal measures are contained in the set of all measures. So of course, if you have more than one extremal measure, you will certainly have more than one invariant measure. On the other hand, if you only have one extremal measure, since every invariant measure is given by some kind of center of mass of different extremal measures, if there's only one of them, then that will be the only invariant measure. In this case, for a circular rotation, the only invariant measure is the Lebesgue measure. The standard measure, the Haar measure on the circle, goes by different names. And this is an exercise that I will let you figure out for yourselves. As you think about this exercise, keep in mind that a measure on a compact metric space, as we proved a couple of weeks ago, must be regular. And a regular measure is a measure that assigns to every measurable set E the supremum of the measures on the compact set contained in E, or if you prefer, the measure of E also equals the infimum on the measures of all the open sets containing E. That means that it is enough to check what happens on open sets. And if this condition of irrational rotation determines uniquely what the measure of open sets are, it will determine the entire measure. Open sets are union of intervals, and you can start by looking at extraordinarily short intervals, and those are a little bit different, a little bit easier to handle. You just have to be careful to get all your quantifiers and epsilon and deltas in a row, and you should be good with this one. Final exercise, you can take T3 to be a transformation from S1 cross the closed interval 0, 1, a cylinder, or an annulus, which is given by circle rotation on the SY direction and don't do anything on the 0, 1 direction. So analyze in this case what are the invariant measures, what are the extremal measures, and so on. And of course you can vary this. You can take a periodic rotation on the circle instead of an irrational one, and you can take a map such as y maps to y squared on the second factor if you so desire, and you can take any other transformation that comes to your mind and try to figure out what are the invariant measures and what are the extremal measures. So our goal is to understand the extremal measure. I think at this point we are maybe convinced that they are more important than just any other measure. And we start off with a definition that tells us when a measure should be called nice. A measure is called ergodic if the transformation that you get by using this measure is an ergodic transformation. So this is a sort of a shift of perspective. What we did before is we looked at the transformation x, b, mu, and t, and we asked for what t is the whole thing ergodic. X, b, and mu were fixed. Now we're saying here's x, b, and t for what mu is the whole thing ergodic. And the theorem for today is a measure, an invariant measure is ergodic if and only if it is extremal. So as our theorem, written right again up here on the top, is an if and only if, we will start with what I believe is the definitely easier direction, showing that if a measure is ergodic, then it must be extremal, and we'll prove by contradiction. So suppose that mu is not ergodic, that means that it admits some invariant set, call it E. Here is the invariant set E. So that the measure of E is some number, call it P, which is in the open interval 0, 1, it cannot be 0, 1. It'll be convenient to call E E1 and the complement of E E0 because both of them play a kind of symmetric role in this game. So note that the measure of E0, of course, that's 1 minus P again. This is neither 0 nor 1. We will define two new measures called mu0 and mu1, where mu0, for instance, of a measurable set E is the measure, measurable set F, is the measure of F intersect E1. This was mu0, wasn't it? Let me start this again. Mu0 of a measurable set F is the measure of F intersect E0 normalized by dividing by the measure of E0. And similarly for I equals 1. So, few details for you to verify. They're quite easy. Mu0 and mu1 are both probability measures, and they are invariant probability measures. Mu is a convex combination of mu0 and mu1. So that looks like showing that mu is not ergodic. Of course, we need to verify one more little detail. Very simple. Mu and mu1 are not the same measure. And now by its very definition, we see that mu is not an extremal measure. So that's it for the easy direction. The other direction is not super hard, and actually there is a pretty short proof if you want to apply the Radon-Nikodym theorem, and that's fine. Only I wanted to choose a proof that is very slightly longer perhaps, but it does have some advantages. It does give us more information, and in particular, it forces us to use the ergodic theorems. So let's review what the ergodic theorems were. We had, in fact, 3 ergodic theorems, and this statement here is a little bit slightly vague because it's not clear which of the 3 we're talking about, but that's on purpose. I want to review all of them. Let x, bx, and mu be a probability space and T a probability preserving transformation, and f is a measurable function, and what kind of measurable function depends on what kind of theorem you're looking at. It's really usually only L1 or L2 that etc. there at the end is not really necessary. What the theorem says is if you look at the ergodic average, let's remember what the ergodic average was. We are looking at j goes from 0 to some number we call n-1. Tj of x is simply the orbit of x, so we're looking at the first endpoint of the orbit. We apply the function f, gives us the value of whatever we're measuring at the orbit, and we simply take the average of that. Well, the ergodic theorem says that this converges to some function that we call f star. We'll discuss what kind of convergence in a second, and f star has the following nice properties. First, if you have an invariant set E, then the integral of f equals the integral of f star. And second, f star is itself invariant. Now, once you have convergence, these are actually not very hard thing to show. So what kind of ergodic theorems did we have? The first ergodic theorem we had was von Neumann's L2 ergodic theorem. Excuse me. So the theorem was von Neumann's L2 ergodic theorem, which says that if f that you start with is an L2 function, then the ergodic average converges in L2, the convergence is L2, and the limiting function f star is also in L2. That was quite an easy theorem actually, and to prove it, all we needed to do is understand that this ergodic average actually represents the orthogonal projection onto the space of invariant functions in L2. The next theorem, which was much more involved, much more difficult to prove, was Birkhoff's L1 ergodic theorem. It was already more general in that it allowed f to be any L1 function, and remember, when you have a probability space, any L2 function is an L1 function, but the other direction is not true. And for any L1 function, Birkhoff proves two things. First, he proves that this ergodic average converges in L1, so now the converges in L1 to a function f star, which is itself in L1. And second, which I think is the last version of the ergodic theorem that we studied, is for any function in L1, this ergodic average converges to f star in L1, and the convergence is pointwise. And that's what we will need today. But it's not pointwise over the entire space. When you talk about things in L1, you know you can always change things on sets of measure 0. It's pointwise for every point x in some set E of full measure. The measure of E is 1. The measure of its complement is 0 equivalent. And we will want to apply this theorem in our setting. Of course, in our setting, we have two systems. We have the system xb mu 0 and t, and we have the system xb mu 1 and t. Even though it's the same x and the same transformation, they're completely different system on account of having different measures. So we're going to rewrite exactly the theorem that's written here, but with I in it, just like this. You have I wherever you can think of putting an I, where I can be either 0 or 1. But there's something funny, because this operator, the ergodic average, does not consider the measure at all. So whether it converges or not has nothing to do with the measure. The set of points where this converges, think about what you're doing here. You're taking a point x, you're looking at its orbit, you're moving it off to r or to c with the function f, and you're asking whether the average converges. That's got nothing to do with measure. The set ei has nothing to do with the measure I. The limiting function f has nothing to do with the measure I. Because this operator doesn't involve the measure, f star and e have nothing to do with the measure, and we will from now on call them indeed f star and e instead of f star sub I and e sub I. With this, equipped with this, we're quite ready to prove the remaining direction of the ergodic or the theorem that says that the measure is ergodic if and only if it's extremal. What's left is to show that ergodic measures are extremal. So again, we'll prove by contradiction. Suppose that you have a measure mu which is not extremal. That means that you can show it as the convex combination of two other measures, say mu 0 and mu 1, where the coefficient 1 minus p and p, neither of them is 0 or 1. Of course, mu 0 and mu 1 here are distinct measures. I forgot to write this down. And as such, we know from the Riesz representation theorem that they describe distinct functionals in Cx star. If you remember, just before we talked about the Riesz representation theorem, actually the first thing we proved about these type of things is that when xd is a compact metric space, if you have two distinct measures, you can distinguish them by their values of integral on continuous functions. Obviously not all continuous function, but there exists some continuous function whose integral will have different value. So it would be convenient to call C0 the value of the integral of this function f with respect to mu0, and C1 the value of the integral of the function f with respect to mu1, and since they're distinct, we will assume, let's say, that C0 is less than C1. Now we apply the ergodic theorem to this specific function f, and we obtain a function f star, which has the following two properties. First, the total integral of f star is the same as the total integral of f, so it's C0 or C1, depending which measure you use when you integrate. And second, f star is invariant under T. So from point of view of Riesz representation, we see that f star also distinguishes between mu0 and mu1. I'm cheating a little bit because f star is probably not continuous, but it's still distinguishes between them as in the first and third point here on the slide right now. And what we gain by doing this, of course, is that now f star is invariant. So let's define a set of point E0 to be the set of all points where f star is less than or equal to C0. Now, what we know is that the integral of f star is C0. But that must mean that the measure of C0 is positive. If the measure of C0 is 0, then the integral of f star, since f star is less than or equal to C0 on the entire set let me start again. F star is strictly greater than C0 on the complement of E0. If the measure of E0 is 0, it means f star is greater than C0 on a measure 1 set, and of course then its integral will be greater than C0. So the measure of E0 must be positive, and all this discussion about the measure of E0 and the integral of f star was done with respect to the measure mu0 only. But what is the measure mu? The measure mu is the convex combination 1 minus p, which is a positive number, times mu0 plus p times mu1. So the measure of E0 is 1 minus p times mu0 for 0, whatever this positive number is, plus a contribution that can't be negative. So certainly we see that the measure of E0, the actual measure of E0, the mu measure that we're interested in, is positive because the mu0 measure of E0 is. Finally, because we know that f star is an invariant function, and we used f star in the manner written right here in the center of the slide to define E0, we certainly know that E0 is invariant under T. So we found a set, E0, which is invariant under T and has positive mu measure. Mu is not ergodic. And this completes the proof of the theorem that says that a measure is ergodic if and only if it's extremal. And if we go back and remember what the ergodic decomposition said, that every measure is the average, in the sense of integrating against a probability function. A probability measure is the average of extremal measures. Well, we can now rephrase it by saying any invariant measure is the average of ergodic measures, and hence the ergodic decomposition. So this allows us to focus especially on ergodic measures, and forces us to look at sometimes at distinct ergodic measures. And the question is, what happens when we look at distinct ergodic measures? So let's talk more generally just about different measures. Suppose mu0 and mu1 are probability measures on the same measurable space xb. These two measures are called mutually singular if they have disjoint supports, precisely if there exist two measurable sets E0 and E1, so that the mu0 measure of E0 is 1 and the mu1 measure of E1 is 1, and the intersection of these two sets is empty. So one example that maybe we can keep in mind, it's a pretty simple example. The measures that we defined previously on the closed interval 0, 1. Mu0 was the measure, or delta 0 was the measure supported on 0, and delta 1, we sometimes call it mu1, was the measure supported on 1. These are mutually singular. One thing to notice is maybe a little bit disappointing possibly, but the set E0 and E1 are not uniquely determined. In fact, any measurable set E0 that contains 0 and does not contain 1 can be used in this game. Now, the reason we're mentioning this is that when we have distinct ergodic measures, they are necessarily mutually singular. So this is the statement of the theorem. You have mu0 and mu1 distinct. Both of them are extremal, which is the same as saying both of them are ergodic. And the claim is that then they're mutually singular. The key to the proof is to use again the function f star from the previous proof. In the previous proof, mu0 and mu1 were just invariant measures. Now we are actually assuming that they are ergodic. And what the ergodic theorem tells us is that when the measure is ergodic, or when the transformation is ergodic, because the function f star that you get is invariant, the function f star is in fact constant. But this is a bit strange, because the integral c0, which we define to be, not c0, excuse me, ci was defined to be the integral of the function f with respect to the measure mu that equals, we know from the ergodic theorem, that equals the integral of f star. But the integral of f star d mu I is just the value of f star. So f star must be a constant function that equals two different values, c1 and c0, and these two are distinct. What is the solution to this conundrum? Well, the solution, of course, is that this apparent contradiction is because f star is not actually constant, but it's constant almost everywhere. And what it exactly means is the following. The set of mu0, I'm reading this line for I equals 0, the set of the set of points, where f star equals c0 has mu0 measure 1. And the set of points where f star equals c1 has mu1 measure 1. Now, of course, these are disjoint sets. There is no point x where f star x equals c0 and c1 simultaneously. So what we see is that decompose the space into two disjoint sets. Each one has measure 1 for its own measure. It is, of course, exactly the definition of mutually singular measures. So what we showed is distinct ergodic measures are mutually singular. And as always, it's good to recap and cast the entire lecture that you heard in terms of examples. Remember the examples that we mentioned in the very beginning of the lecture. We had the transformation T1 from the closed interval to itself given by x squared. We had the transformation, T2, which was an irrational rotation of the torus. And we had the transformation T3, which was a irrational rotation on the cylinder that rotated the cylinder in the S1 direction and did nothing in the second direction. And you can vary this, you can do something in the second direction, etc. And you can now look at what the ergodic theorem means to those and everything that we did. I definitely encourage you to review this. This is a really important theorem. We'll see it a little bit in application, the ergodic decomposition theorem, but we won't have much time to use it a lot. So it's definitely a good idea to review it now rather than banking on it showing up many times in this course, being that the semester is already 2/3 of the way over. As always, shoot me an email if you have any kind of questions. I'll be happy to try and discuss it with you. This wraps up the 5 lectures that we have about the ergodic decomposition theorem, and we are moving into a completely different direction with the next lecture. And until then, goodbye.